Well, thank you for coming out today and to listen to an old guy talk about an even older computer. We are here to talk about the ENIAC. Most people in our field, of course, have heard of it. Most people don't know much about what it is. You may have heard it was the first computer, or you may have heard it wasn't the first computer, or you may have heard the patent got invalidated because they stole all the ideas. The reality is that it is a very rich history, and it is a very interesting machine, and it was a very, very influential machine. Now, we're not going to really go into all of the history aspects of it today. We're going to talk more technical terms about it. In particular, we're going to focus on this simulator that I wrote. The motivation was simply, I wanted to understand how the ENIAC worked. And I felt the best way to do that was to write a simulator of it and to get down to as low a level as I could get. And so that's what we're going to be talking about today. So let's see if the clicker works. Aha! So this gives you kind of the usual rundown of what the ENIAC was all about. The story essentially is, during World War II, as artillery manufacturers are producing new guns, new propellants, new shells, we need to calculate the tables so that when you're in the field, you're not solving differential equations to figure out where to point the gun. You want to have this table that says, okay, if I'm shooting in that direction, the wind is blowing that way, it's that far away, and the humidity is this, I need to point the gun there. And these tables took a tremendous amount of computation. And of course, the way you compute something is with a computer. Except the thing is that in the 1940s, the word computer was a job title. These were people doing computing. The US government, for both this purpose and for the purposes of code breaking, sought to hire as many mathematicians as they possibly could. Yet with a war going on, of course, all of the young men who had just been studying mathematics were off at the front. So we have this wonderful competition between divisions of the government to hire all of the young women who had been studying mathematics. And they're doing these calculations mostly by hand on adding machines. And one of the researchers at the University of Pennsylvania named John Mauchly came up with the idea of essentially building a machine that was strapped together a whole bunch of adding machines. And he recognized that it would be even faster if you used vacuum tubes. And so this was the birth of the ENIAC. Being a war, you make a proposal to the government that can help, and they say, great, have some money and go do it. Whether or not they could have gotten the money in peacetime is another question. But it began in 1943. By early 1944, they had some prototype stuff running. By the summer of 1944, they pretty much had it worked out what they were going to do and had turned over a lot of the work to other engineers and technicians for building it. It wasn't until late 1945, however, that the machine was completely finished. So it didn't actually get used during World War II. But interestingly, the first task it had was a project that was also sparked by World War II. The Manhattan Project, Los Alamos had some heavy calculations they wanted done. And so they came out during the winter of 1945 and used the ENIAC to do some of those calculations. One of the interesting points about it that a lot of people will make is that you couldn't program it the way we're used to programming modern computers. You had to rewire the machine to program it. And that was true as it was initially built. But here's the thing. If I can wire a solution to any problem, why can't I wire a solution to the problem of being a CPU? And that's what they did. So in 1948, they implemented a CPU on a traditional and sequential instruction execution CPU, and it was used that way until its retirement in 1955. So this is actually going to come back and be something important in a minute. As you might guess, it changed the balance of performance on the machine quite a bit to do this. All right, so this is the famous picture of the ENIAC that was taken as part of the publicity. This was taken and released in the press release when it was dedicated and announced to the public in early '46. And you can see in the picture that this goes back a long distance into the room. You've got some people standing around to give you a sense of scale. The whole machine looks something like this. Now, obviously, this is a bit too small for most of you to see, but if you want to come take a look at it after the talk, you're welcome to. This is a small 3D printed model of the ENIAC. And these stand-up pieces that the soldier is standing by in that picture are the switch panels that were originally put on for function tables. And that's where the instructions were stored when it was later run as a conventional computer. Right here we have punch card input and output, the only I/O on the machine. No screens, no mice. These are the two guys that really kind of led the project. The first one that I mentioned before was John Malkley on the left. He was a physicist at the University of Pennsylvania, and he was very interested in a variety of kinds of problems that were extremely numerically difficult problems. One of his big interests was weather. How do you predict the weather? Well, we know the differential equations for fluid mechanics, but if you're going to do a 24-hour forecast by hand, it's going to take you a lot more than 24 hours to do it. So this is one of his motivators in this. The fellow on the right, J. Presper Eckert, was a graduate student at Penn when they met. In fact, Eckert was teaching a sort of workshop on electronics that Malkley took. And Eckert was, let's face it, an engineering genius. He was one of the top electrical engineers you can imagine. He invented all sorts of cool ideas and really put it on extremely solid footing, and it was one of the few reasons the machine was successful. We have these wonderful statistics that always get quoted. And the second one on that list, it had about 18,000 vacuum tubes. That was more than anything before it. In fact, when they first proposed the machine, they had proposed a slightly smaller version that would have about 5,000 tubes. The government folks went to the experts, mostly MIT, and said, "What do you think of this proposal?" And their response was, "There's no way that machine will ever run. The tubes will burn out too fast." But Eckert realized the mechanisms that were involved in a tube burning out and was able to design around it. He was able to operate the tubes in a way that would minimize their burnout and, furthermore, to extend the usage life of it as their parameters changed over time. So these kinds of design characteristics were really what Eckert brought to it. As you can see, it had the blazingly fast clock of 100 kilohertz. Okay, now that's not gigahertz, it's not megahertz. A kilohertz is 1/1,000,000th of a gigahertz. This gives you some sense of the speed of this machine. It took about 200 microseconds to do an addition. That's why you often will hear quoted the figure 5,000 additions per second. As we're going to see, that's not the most accurate way to look at it because it was a very parallel machine. These last 3 points here, I really love those. Being someone who grew up in a world of 5-volt TTL, thinking about a computer that uses 150 kilowatts of power with 29 distinct power supplies and 78 different DC voltage levels is kind of frightening, especially when you look at the schematics and all the numbers are 3-digit numbers. You know, it's like, this one's negative 290 volts, and this is positive 540 volts. And it's like, okay, I'm used to 5 volts that I can touch and be safe. But this obviously was quite a beast of a machine. The basic architecture of it is consisting of these units. Now, what you have, and you may have seen a little bit of this in the picture, are these racks that go around the room. Now, they're not quite our standard modern 19-inch racks, but these racks are roughly 2 feet wide. So they're a little bit wider than our typical 19-inch racks. They're about 8 feet tall, and there's 40 of them. So if you spread this thing out, you would have a wall 80 feet long by 8 feet tall. And each one of these racks is a unit of the machine. It has some functionality relative to the whole machine. And this is kind of an inventory of those units. The bulk of the actual computation is all taking place in the accumulators. And that's what we're going to focus most on today. But we also have a high-speed multiplier that took 3 racks. It was built around good old-fashioned multiplication tables. The same ones you learned in 2nd grade, because it was a base 10 machine, worked in decimal. There was a divider square rooter. The function tables that I mentioned before, which were connected to these switch panels. And then the interfaces to the I/O devices, the punch cards. Now, this is how the machine was laid out from kind of a top-down view. And you really can't read it very well, but these are the labelings of all of the units. Over here we have the initiating and cycling units. The initiating unit, its primary role was twofold. One was to control the sequencing of power when you started it up. And then it was also to sort of synchronize the initialization of a program and the interaction with cards, both punching and reading. The next unit, the cycling unit, is basically the clock. We have the master programmer I'll say a little bit about. And then around here are intermixed the accumulators, the multiplier, divider square rooter, and so on. This space inside of it was 32 by 16 feet. Now, they rearranged the layout slightly when they moved it to its permanent location in Aberdeen, Maryland. And they had a newly constructed space for it when they moved it. It was one of the few spaces in the area that had air conditioning. So late in the life of the ENIAC, people started dragging their desks in there during the summer and using it as office space. You know, no matter how impressive, there's still going to be good old human nature coming into play. Now, some of the things about it that were really unusual from our modern eye is that there was no concept of memory the way we think about it. We think in terms of a large array of individually addressable locations that are read and write. The ENIAC did not have that. The only volatile memory you had available were the accumulators. So you basically had 20 10-digit numbers as your volatile memory. So to kind of think in terms of how it was like programming this machine, think in terms of restricting yourself to 20 integer variables. If you can't solve atomic bomb problems with 20 integer variables, you're not good enough to program the ENIAC. Okay, that's a little overstated, but you know, kind of get the idea. The other big thing about it that I like to point out is how parallel it was. All 20 of those accumulators could be operating simultaneously. So even though a single addition would take 1/5000th of a second, you could be doing 20 of them at the same time. So it was a very, very parallel machine. In fact, I love this quote by Lemmer. This was a highly parallel machine before von Neumann spoiled it. And this reference is to the conversion to sequential instruction set execution, because von Neumann was actually one of the key drivers behind making that conversion. Lemmer had used the machine for some interesting number theory stuff and had really taken a lot of advantage of its parallelism. And so he was kind of disappointed when they switched it up and made it purely sequential. The other thing that I'll point out, and this may not mean much to some of the younger folks in the audience, but this basically is like a data flow machine. Okay, now if you go back to kind of the 70s, 80s time frame, that was one of the big buzzwords in the industry, was data flow. And that was going to save us from all of the problems that we had with various bottlenecks. And it was the new thing. Well, it wasn't really all that new, because the ENIAC was a data flow machine. And the idea of data flow, if you're not familiar with it, is each unit, when it completes an operation, it sends a signal that can initiate the next operation. So in effect, you do an addition not when the instructions say, but when the two data values that you're adding become available. So it's driven by the availability of the data, not by the instructions. And that's the way the ENIAC was operated. So the parallelism, of course, is a big deal because I'm trying to understand how the machine works. I'm trying to get a feel for what was it like to program. What were the traps involved for programmers when they were dealing with it? We're all used to the problems involved with parallelism. The easiest way to make a programmer cringe is to say it's a timing problem. Anytime concurrency gets involved, we all shudder and kind of grit our teeth and go, okay, I can do this. So I wanted to get a feel for what that was like on the ENIAC. Well, obviously, if I really wanted to truly get the experience, I would need to build some parallel hardware for it. And while it's still one of my to-do list items, that didn't seem all that practical for a first approach. Of course, I could just write code, ordinary sequential code, and just sequentially go through each one of the units doing what they do. But I went ahead and decided to kind of take the middle ground and go ahead and use the concurrency we have available in a lot of our languages and to hopefully take advantage of whatever parallelism the hardware underlying it gives me. And so that made it a very natural fit for the Go routines in the language Go. Of course, I could use conventional p-threads or something like that, but Go's model is quite clean, and I liked the idea of having the portability that it would also give me, so that was one of the motivating factors there. So what happens is each of these units in the machine is simulated by usually 2 Go routines that are operating in parallel. And the way that works is the 2 routines are handling different sets of input. Now, to give you a little bit of sense of what we're getting at here, remember we said you rewire the machine to program it. So that means that if I want this adder to be adding a value that comes from over here, somewhere I've got to have a cabling connection that brings the data from the source to the destination. That data, as it's coming in over some kind of a terminal on the destination, is just going to be a sequence of pulses. And so these pulses are the input to the units. There are pulses that indicate begin an operation, and then there are pulses that indicate data. Those are the control and data pulses that go into one of the Go routines. That routine doesn't do very much except set some state variables for the unit. Kind of represents the internal flip-flops of the unit. In fact, if you go through and read some of the technical documentation and you look at the source code, you'll see a few places where there are variables that are named after certain circuits in the original. The other Go routine is taking the input from the clock, which is another series of pulses. Originally, I implemented this as 1 routine per unit, and I realized I had a little bit of a problem because the result of a clock signal could turn into a control signal that I would transmit that would come right back into one of my other inputs. And unless my communications channels had some buffers in them, I would have deadlock. And if I put buffers in it, how could I be sure that things were synchronizing the way they were really meant to? So I went ahead and split it into the 2 units for that reason. As I said, that pulses are transmitted. Now, this is another bit of Eckert's genius. He said, I'm going to make all the pulses the same. Control pulses, data pulses, clock pulses, they're all going to have the same shape, the same characteristics. The idea is that there's no reason I can't use some data as a control signal. And when you open up that possibility, you get the possibility of conditional flow of control. And that's what makes it Turing complete. So those fit very naturally into a channel model of communication. In fact, the way it's set up is that messages over the channels represent pulses. In the case of the control lines, where there's only 1 signal being transmitted for a given line, it's just a 1 or a 0 in the message. In the case of data, the terminals are actually 11 lines. You've got 10-digit lines and a sign. Similarly, the clock trunk has 10 or 11 signals. So those, I decided rather than create the skew that would be involved with sending a different message for each pulse, I basically take the 11 lines and treat them as bits of a word and just transmit an integer. So that becomes the way in which the data transmission is emulated. And again, the idea is to get as close to the way the real machine worked so that in looking at its behavior, I could understand what was going on with the real machine. And if I have a little bit of time, I'll mention some of the results that came out of all of that. So here's the clock. It's a rather interesting clock in a lot of ways. Remember I said it was 100 kilohertz basic clock. So each of these time units here is 10 microseconds. A sequence of 20 of them constitutes, that's the word I'm looking for, a period that's known as an addition time. That's why we say that additions take 200 microseconds. And in that, we have a set of pulses. Here's 10 pulses. That kind of fits since we're using base 10. There's interleaved between them a set of 9 pulses, and we'll see how that's used in a minute. We've got 4 sets of signals here with 1, 2 with 2, and 1 with 4. It turns out that with those, I can construct any digit I want. If I want the digit 5, I turn on the 4 and the 1, or the 2 2s and the 1. Got a few options there. There's this 1' pulse, that's kind of special. We probably won't have time to get into the details of it. But the really interesting one in this is this pulse right up in the top. It's labeled the central programming pulse. This is kind of what we would think of as the clock in more modern terms. This is the rate at which operations are taking place. So the thing that initiates an add, the thing that starts a multiply, it's always going to be synchronized with that central programming pulse. So in the simulator, basically what I've got is a set of channels that go directly from the cycling unit, the clock generator, to each of the units in the machine that consumes clock. And so that's done as a real simple little fan-out kind of routine that just says, OK, I'm going to receive a message. I've got a list of places to send it. I'm just going to send it to all of them. And it turns out there's also some handshaking I'll explain in a minute. So here's an example of the way in which we connect the signals. Now, this particular photograph was taken from an exhibit at Fort Sill in Oklahoma. They have a subset of the ENIAC on display there. Unfortunately, they haven't exactly hooked it up in a way that is real. They've just plugged a bunch of wires in and, gee, look. And one of the things that is kind of inaccurate is the mixing of these different types of trays. In practice, the ones with these individual connectors, the ones that have the alternating black and white backgrounds, those would run across the tops of the control panels. Sorry, take that back. Those run across the bottom of the machine. The other ones with these multi-pin connectors would run across the tops of the control panels. The multi-pin connector ones were where you carry data, and then the ones with individual pins like these were where you carried control signals. Now the interesting thing is these are buses. You can plug lots of different connections into one of these things that ties to all of these other connections. A bunch of them might be transmitters, and you basically get sort of a wired OR behavior. They might be receivers, in which case they're just getting whatever one of the transmitters is doing. So the fact that these configurations aren't fixed, that the programmer can choose whatever they want for the configuration, means I've got to have a fairly general mechanism in the simulator to allow you to sort of connect as many transmitters and receivers as you want to one of these buses. And so that little structure turns out to have been kind of a fun part of the project, where I end up with this collection of these trays. And so kind of matching the physical machine, there is an implementation, I think it's 10 or 20 of each type of tray. And within the tray, what you do is you have an array of connections that have been connected to it identified as transmitters. And then you just simultaneously listen for a message on all of those channels. Any one that you get, you then turn around and pass it on to all of the receivers that you've got. And so when you have the commands that do the configuration, saying plug a wire from here to here, that goes into the trays as, here, I'm a transmitter to this, and here I'm a receiver to this. Now, there's one aspect of this that is slightly different than the original. In the original, the wires, in principle, could carry signals in both directions. Now, it was never really used that way, and so I figured it was safe to go ahead and, in the simulator, treat each one of the channels as unidirectional. So this is kind of the discussion about how those trunks work. Now let me mention the handshaking. In the original machine, when the clocking unit, the cycling unit, transmitted, say, a central programming pulse throughout the machine, then of course each unit would respond to that. It would potentially, as a result, send out other signals. Now, the design of the machine was such that before the next pulse, the next cycle of that 100 kilohertz clock, we could rely on all of the circuits having finished what they were doing with that first pulse. If you're writing code running on a time-sharing operating system, it ain't so predictable. And in fact, that turned out to be an issue that I ran into. On some platforms, it seemed to run quite stably. On other platforms, it would fail tests. And digging in, I was finding things like, oh, this signal was happening before this signal when it should be the other way around. So I swallowed hard and said, okay, I'll go ahead and implement a handshaking mechanism. So the idea is that if I receive a clock signal, I'm not going to send back the acknowledgement until I have finished with anything I'm sending and gotten the acknowledgements for those. And then I'll be able to send my acknowledgement back. So that ends up actually throttling the speed of the simulator a bit. And some people are a little surprised to find that the simulator actually runs slightly slower than the original machine. Yes, the original machine was quite slow, but this simulator is even slower. But again, it gets down to that working at a very low level. Okay, so how do the accumulators work? As I said, this is where most of the computation takes place. And the way it is set up is each accumulator stores 10 decimal digits. And it does so by using a 10-stage ring counter. And the ring counters were implemented in these plug-in modules that would plug into the back here. And so you would have on the machine a vertical line of 10 neon lamps, one of which was illuminated. That was the value of that digit. Then you had 10 of those columns next to each other. It was the 10-digit number. And then we also had a sign, a plus or minus sign. And of course, you look at that and think, aha, they're doing sign magnitude. Nope. They've got a sign and they're doing tens complement. It's kind of a weird combination. But of course, that means, like two's complement, additions don't have to pay attention to sign. They do the right thing. The inputs to the accumulators are labeled by these Greek letters, alpha through epsilon. Each one of those represents a channel over which I can take these 10 digits in parallel and add to whatever is in the accumulator currently. The outputs are labeled A and S. The A output is an additive output, and the S output is a subtractive output. The idea is that if I want to add, I'll transmit on the additive output, and whoever receives it will get that added to their current value. If I'm subtracting, I'll output on the S output, and then whoever receives it will get the difference. And the way it does it is by sending the number as it's stored on the A output and sending the complement of the number over to the S output. For each of 12 different operations you can trigger on an accumulator, you've got switches that let you set what that operation is going to do. And basically, you can either say, I'm going to receive on one of the inputs, or I'm going to output on one or both of the outputs. Or, and you got to love this, they've got a no-op. It turns out that no-op is actually used fairly often on the ENIAC. You've got a couple of other controls, one of which says, if I'm transmitting, do I clear the accumulator after? That same control, if I'm receiving, I actually get an extra 1 added in. And that has to do with the 9s versus 10s complement. You may remember go all the way back to your freshman year in college when you were taught about 1s and 2s complement. 1's complement, you flip all the bits. For 2's complement, you flip all the bits and add 1. Same sort of thing happens with 9 and 10's complement. To get from 9's complement to 10's complement, you just add 1. And so that correct setting is about adding an extra 1 for that. The other thing we've got is a nice little repeat mechanism. So if I want to add 3x to y, then I don't have to set it up as 3 separate operations. I can set it up as one operation in which x is transmitted 3 times and y receives 3 times. So small integer coefficients in your equations don't actually have to go through the multiplier. You only need the multiplier when you're multiplying 2 variables together. So here's how the whole thing works. This gets us into those pulses I was talking about. These are the 2 lines from the clocking diagram with the group of 10 and the group of 9. Now, if I think about a digit, say its value is 4, then I want to transmit 4 pulses out the A side for that digit. I want to send the 9's complement of that, which would be 5 pulses, out the S side. The reality is I'm always going to be sending 9 pulses. It's just which of them are going out the A and which are going out the S. So the cleverness is, well, what we'll do is we'll take the value in that digit, feed 10 pulses into it. That causes the ring counter to go all the way back around to where it started. And in the process of doing so, at some point, it's going to go from 9 to 0. And what happens when we go from 9 to 0? We set a carry. And it turns out that if you think about it for a second, the carry is exactly when I need to switch from outputting on one of the terminals to switching to the other. So we start out sending out the S port. As soon as the carry hits, we switch and send the rest of the 9 pulses out the A port. And this is how we read information from the accumulators. It's easy enough to figure out how to make it add, but how do you read the information out? That wasn't as obvious. People were used to using these sorts of counters. In fact, Eckert had a lot of experience. People doing nuclear research had these decade counters that they were using for measuring radiation. But of course, the information that you got out of the counter was always a human being looking at the lights. How do you pull the information out and use it somewhere else? This really clever approach is what they used. And what I'm going to do right now is, in the simulator, illustrate that in operation. So here is an image of the simulator. What I've done is I've sort of zoomed in on one section of the machine. Depending on what you're doing with it, this view of the whole machine is a little bit more impressive, especially when the lights are moving and doing all sorts of fun stuff. But right now we're going to be looking at just a few parts of the machine. In particular, the leftmost unit in this figure is the divider square rooter, and then immediately to its right are a set of 7 accumulators. And the first 3 of those accumulators are what we're going to be using right now. The other thing I'll point out here is that in the lower left-hand corner of this image is a representation of a control box. In fact, it's got some photographic remnant of the real thing. And this is what the control box looked like. This is a 3D printed reproduction of it. This one is actually set up to be able to plug it into a simulator running on a Raspberry Pi and actually control the ENIAC. The neat thing about this was it really showed a great deal of foresight into the questions of debugging. One of the most important things that this lets you do is single-step the machine. In fact, this switch lets you control what level of granularity your single-stepping is doing. And it had a long enough cord you could walk around the whole machine, so you could walk up to any accumulator and just sit there and go, aha, there's the mistake. So what I'm going to be doing right now is doing the on-screen version of that right down here. And so this is how I'm going to be controlling it. Right now I've got the clocking mode set that every time I hit the pulse button, 1 addition times worth of activity is going to take place. So initially I'll hit the initialize button, which sends out a pulse that is meant to start the first stage of the computation. And in this case, the first stages are loading some values in. Now if you look carefully, the first accumulator, that second panel here, now has a couple of values in it that weren't there before. The first digit is moved up 1 place, and this next digit over here is moved up 5. So we've stored the number 15 in this accumulator. I'm going to hit another pulse, and what's going to happen is, in parallel, I'm going to load a value into both of these. And in this case, the value loaded into each of those is 27. So we've got 15 in the first accumulator, 27 in the other 2. And what I'm going to do now is go through that step by step of how it transmits from one place to another. The additive output's going to go into one of the other accumulators and the subtractive into the other. So I'm going to simultaneously be computing the sum of 15 and 27 and the difference of 15 and 27. So let me switch the clock now to the single pulse mode, and we now begin this sequence. So here, if you look at the one on the left, all of the positions have moved up 1 spot. That's one of those 10 pulses. And as we're going through those 10 pulses, you see that some of these things are also causing things to climb on the other 2 accumulators. And the lights underneath are the carry lights. So they tell you when it's going from one to the other. Once we've resolved all of the carries, we now have in the second accumulator a sum of 42, and in the third accumulator the difference of 12. So when you're operating the ENIAC, that's basically the way you're doing arithmetic, is you're counting pulses on a per digit basis. And if you can't figure out what went wrong, you've got your debugger. I actually kind of like this kind of a debugger. Wish we had this on real computers, or modern computers, I should say. I sometimes tell folks that, especially my students, that it's not a real computer if there's not blinking lights. I mean, let's face it. We haven't had good computers since the PDP-11, have we? Okay. So the next piece of this that I want to mention is the master programmer. The idea here is that, yes, it's fairly easy to build a sequence of operations where the output terminal from one operation triggers the next operation. But how do you go about doing repetition? How do you do conditional operations? The master programmer is the equipment they put in for that purpose. Now, it's not as completely general as we usually think of in terms of a typical stored program type scenario, where you've got a jump instruction and you can organize them however you want. But it was very flexible. It contained 10 counters of 6 stages each. These counters, these 6-stage counters, represented phases of a computation. And so every time you advanced that, you would go to the next phase of the computation. For each one of those phases, you had counters that you could set to be a simple limit on how many iterations to perform. Total of 20 digits worth of counters, and you could kind of reassign them to different ones of the 6-stage counters as needed. So you could really build these very complex nested loop structures if you wanted. Another neat thing that happens is we have these interesting cabling structures here, but we have special adapter cables that will take one of those multi-pin connectors and break it out into 11 of the individual control connectors. And since the pulse shapes are exactly the same, we can take a digit output and use it as control. So for example, if I take the sine output, I can use that to discriminate between positive and negative. So the conditional values that they used, in fact, the term they used in the manual was magnitude discrimination, was to determine the comparison of two magnitudes. And it was typically, or one of the most common forms was in terms of the sign. Was it positive or negative? So by introducing a data signal into the control structure, you could generate a control pulse only if a certain result was negative or only if it was non-negative. And by doing that, you got conditional branching. And that, of course, as we know, turned out to be the key thing. Once you had that, you had Turing completeness. And that's why they were able then to look at building an instruction set decoder. Well, in fact, they actually had some clever use of the master programmer in the original thoughts for the instruction set decoding, where they would use what amounted to the 60 different outputs from the stages as, in a sense, the instruction decoding. So if you had an instruction set of 60 or fewer instructions, you could implement it directly on the existing hardware. Now, it turns out what they actually did in practice was they decided they wanted a more rich instruction set. So they added another component that would take a 2-digit number and break it out to 100 connections. And they called that the converter unit. So that's what was actually deployed. The other neat thing about this is that if I take, instead of a sign, a digit and feed it into one of these 6-stage counters, I basically get what, any old Fortran folks in here? What we call a computed goto. Essentially, you take the value of this integer and it selects one of 6 possible actions. There's an example in the technical manual that takes a pair of these 6-stage counters and divides it into 2 groups of 5, and then you've got now 10 options from a single digit. So one example of using this is calculating, say, a table of squares. And I'm not going to go through a lot of the detail of this. I'll just suggest that if you take a look at the slides later and you want to kind of figure out how this works, we're not actually squaring anything. We're just using everybody's favorite relation from high school. X plus 1 squared is x squared plus 2x plus 1. And neat little things like 2x, well, we just use the repeat mechanism on the accumulators to do that. Okay, this, by the way, is how you would wire up that problem. This is, in effect, your source code. The switch settings are indicated by values in these boxes, and then the wiring is indicated on the top and bottom. The data trunks up here, and the control trunks down here. And this is the way in which you would typically specify a program. They had a few other variations on this, but this was a very direct one because now you could take that, walk into the machine room, and wire it up. And one of the ways this was frequently done was one person would stand in the middle of the room with the papers and call out, accumulator 12, program 3, switch setting alpha. And there would be a person standing at that accumulator and turn the switch. And you would have this whole room full of people programming the machine that way. As you might guess, bugs in the form of plugging in the wrong cable or setting the wrong switch, those were pretty common. Okay, I've already really kind of mentioned this, so I don't want to spend too much time on that. I do want to mention a little bit about how this user interface came about that I showed you. What you saw was just the graphical part of it. There's actually also a command line interface, which is really, from the code's perspective, the main interface. And it's a very primitive sort of a thing. You know, I am an old-timer in that regard. Why type 3 characters if I can type 1? Let's face it. There's nothing wrong with a variable called I. So it's got very simple single-letter commands and abbreviations to refer to the unit. So for example, if I'm going to set a switch setting, the command is S. I'll specify which switch and then a value. And so you get this nice little 3 fields in a line, which looks a lot like assembly language. In fact, I was comparing notes and discussing this work with another person who had done an ENIAC simulator, and he liked that format, so he converted his to use it. And between the two of us, we started calling it the ENIAC assembly language. So it turns out then, if you want to have a configuration file that wires up a whole setting, it's just a file you read that look like commands that the user's typed. So nothing special in terms of configuration files. So how's the graphical stuff done? Well, a long time ago, I reached the point where I decided I was done dealing with graphical libraries. Every one of them is different, none of them are any good. I'm going to let TCLTK do the job for me. So all I do is create a child process running Wish, which is the windowing shell from TCLTK. I set up a couple of pipes, one that becomes its standard input, one that becomes its standard output. When I want to do something on the screen, I just shoot commands down, and it happens on the screen. When somebody pushes a button on the screen, it just sends back a message that happens to be exactly the same format as what would happen if you typed a command at the command line window. The beauty of this is it's completely portable. TCLTK has been ported to virtually everything. And I don't have to think about anybody else's graphical environment. I don't have to think about anything. It does it all for me. So this has kind of become my standard way of doing graphics. The other thing that's kind of interesting about this is, where did these images come from? There's no actual photograph of the machine that looks like that. But there are lots of photographs of different bits of the machine. So I actually went through, scoured many hundreds of photographs, and found like the best photograph of this part right here, and this part right here, and this part right here, and then pasted them together into units. And then I wrote a custom ray tracer to generate the depth. So that's how that perspective image came about. All right, let's see. I believe, yeah, here's a couple of examples of it running. My favorite one is the one on the right. If you remember a little device called the Chip a few years ago, it was a Kickstarter. They ended up closing up. Little ARM machine. That's it running on this little pocket thing. I meant to bring it with me and forgot. Now, I promised this would kind of come full circle. So I need to talk about one more connection between Go and the ENIAC. And it starts with this guy right here, Harry Huskey. Huskey is probably one of the most influential and least known figures in the history of computing. He only passed away recently at the age of 101. His role in the ENIAC was as the designer of the interface units between the ENIAC and the punch card, card and punch. Later, after the design work had been done and the machine was under construction, the team began working on their follow-on project, the EDVAC, and he was a part of that. After the war, he took a sabbatical, and he went to England, where he was at the National Physical Laboratory. And if you've followed the history of Alan Turing, you'll know that's where he went after Bletchley Park. Well, Husky was intrigued at some of Turing's architectural ideas for building computers, and he pushed the folks at NPL to build a sort of small pilot version of this work. Well, a project kind of started and fizzled while he was there, but after he left, that same project got resurrected and produced a machine that we now know today as the Pilot Ace. Very interesting architecture if you study it. After that, he comes back to the US. He goes out to California and is the lead engineer on the development of a machine called the SWAC, the Standards Western Automatic Computer. The National Bureau of Standards built 2 machines in these early days, and he was the lead for the one on the West Coast. After that, he joined the faculty at the University of California, Berkeley. Now, while he was at Berkeley, he had several notable students. One of his PhD students was Nicholas Wirth, the person who then went on to do the languages Pascal, Modula, Oberon. One of his master's students was this fellow right here, Ken Thompson, who, of course, as we know, went on to work on the Multics project at Bell Labs. Then, when Bell Labs dropped out of Multics, he said, let me find something interesting to work on. And as he puts it, he found the little-used PDP-7. He was going to do space exploration type stuff, well, space war games, and decided, I need to build me a little operating system. And that was Unix. And of course, we all know from there, he had developed the language B. Dennis Ritchie added types to make it C. Before he retired, Ken was working for Google as one of the key developers on Go. So that's how it actually comes all the way full circle. All right, any questions? All right, well, I think we've used right at an hour, so thank you very much, and have a good rest of the day.